Good afternoon, everyone. A very warm welcome to the second session of today's program. And we have with us Professor Sripad M. Garge with us. And it's my pleasure to introduce Sripad to you because he's an old friend. Old, don't go by the gray hair, not old man. The friendship is old, the man is young. Uh, and formal introduction goes like he works in area of algebraic groups. He's a professor at IIT Bombay. But let me tell you something formal about this. You know, uh, being a good mathematician doesn't imply being a good teacher. Everyone knows it. Must have experienced that. But the special thing with Vipad is that he is a very good man as well as a very good teacher, and you can't say which aspect of him is better. And some of the topics which I know today were first introduced by Sripad only. Includes, I think, something about Dorai in the sense of algebraic. And the second one was algebraic case theory when I still remember those by him about basically algebra is a full picture and I believe that you all will enjoy the talk. I hand over to
Thanks a lot, Mukund. It's very kind introduction by you. To tell everyone, I was very happy when Mukund asked me whether I should be able to speak on this, and I grabbed the opportunity with both the hands. Meaning once we were together in HRI, and I just like Mukund also said, I also remember it may seem very surprising, but I learned some of the very basic things from him. So I learned about Dedekind cuts from Mukund, and if somebody asked me how did you learn Dedekind cuts, I always say that it was my friend Mukund who introduced it to me. Mukund is very savvy in real analysis, and he knows basic analysis very well. And I had a very superficial knowledge. I was always, and I am still interested in algebra. So it's unfortunate that we have to focus on one subject at the cost of some other subjects, and then the good thing is that we have nice friends who from whom we can learn these things. So I still remember how Mukund had painstakingly introduced the Dedekind cuts to me, and that is one memory that I always cherish. Then I visited him in Delhi University a few times, but meaning once our things diverge, once we have more responsibilities, then it becomes very difficult to keep in touch. And so I was very happy when he asked me to speak on this. Also, elliptic curves is something which I really like. Meaning, Mukund said that my interest is in algebraic groups, and elliptic curves are some kind of algebraic groups, but moreover, even with number theory, they have a nice connection. So maybe I should just start my lecture by starting to share the screen.
yeah.
So do you see me somewhere else? Meaning, of course, you will see the screen that I am sharing, but is there a way to see me? I was just wondering about it, because I will be making several gestures, and it will be nice if you could see me as well. I don't know what you are seeing. So okay,
I think you are using your laptop to log in with your mobile as well.
okay.
So it will show as two users and maybe then can focus the mobile camera on face.
Oh, okay. No, but there might be some sound issue and so on. All right. So if you are seeing my friend's picture right now, that is good. And I will now shift the screen and go to the slides. So please let me know if you see the slides, and the slides are visible or they are not yet visible.
Yeah, visible.
Very good, very good. So this is about elliptic curves. This is going to be a very brief introduction. Elliptic curves is a very well-known topic in number theory, and ideally there should be a whole one-year course, not even a one-semester course, but a whole one-year course to talk about elliptic curves. Only then we can do justice to the whole theory. But of course, meaning when you have some definite object in your mind, then you would like to know whatever is necessary from the theory of elliptic curves, and then go ahead to do the things that you really want to do. So if we go by the name, of course, an elliptic curve has to be a curve. And one may wonder what are elliptic curves. So best thing would be to give you some examples. One may ask, what is an elliptic curve? And here is an elliptic curve for you. So, we see the elliptic curve in as a picture in R2, and we see that there is this horizontal x-axis, there is this vertical y-axis, and we have a curve which intersects all the four quadrants of the plane R2, and in a very nice and symmetrical way. In fact, elliptic curves are supposed to have lot of symmetries. So maybe I'll talk about these symmetries when I come to elliptic curves or complex numbers and rational numbers. But we see it very nicely here that there is a very obvious symmetry that, this is the symmetry of reflection along the x-axis. If you reflect the whole picture along the x-axis, so the plane half plane which is above the x-axis goes below, and the one which is below comes above, then the elliptic curve is sent to elliptic curve. So this reflection will restrict to a reflection on the elliptic curve. It restricts to a symmetry of the elliptic curve, and the very standard reason for that is that whenever you have x comma y as a point on the elliptic curve, then x comma minus y is also a point, right? So you have x comma y might be a point somewhere here, and then below that you would have x comma minus y, which is obtained simply by drawing a vertical line parallel to the y-axis through your point, and it will hit the curve somewhere below, and that will be precisely the point x comma minus y. So both these points lie on the elliptic curve. This is one very standard thing that we immediately observe, at least for the curve that we have here. Let's see if we can get some more examples of elliptic curves. So here are some more examples. The picture that I showed you earlier was of the curve given by y square equal to x cube minus x minus 1, the picture that is here on the right hand side. Okay, that was the picture that I showed you. And here on the other side, we have another picture given by the equation y square equal to x cube minus x. This is also an elliptic curve. It's a single curve. Although when we look at it in this picture, it may seem like there are two connected components. You have one somewhat elliptical shape, and then the other is a curve which is it is more close to the vertical line than the curve that we had seen earlier. So you may want to think of this as the family of curves which is obtained from the curve which we have here on the right hand side with only one connected component, and resulting finally in the curve that you have on the left hand side, where the pinch that you have here, that is being brought together. So these 2 points, they are being brought together, and ultimately that's where the curve cuts, and so you have two connected components. But meaning they say that pictures don't tell the whole picture. So even if you may have some picture and that doesn't tell you what is really happening, because these are pictures of real points. And often, whenever we consider the curve or in general any variety, we look at the complex points or the points over algebraic closure, and that is where we should concentrate at. This is not something which is going to tell you everything about it. So we should consider more and more pictures. Whenever we learn a new definition, it's also good to see some objects which do not satisfy the definition. So I'm going to show you a picture which has two curves. Here we have, this is given by y square equal to x cube. This is also something which is familiar to you. By the way, I should tell you that here we always have on the left hand side of the equation, the part is always y square. You may have a general part, but everything like every such equation can be brought to this equation in a nice way. So we are going to consider only equations of this type, and y square will tell you that whenever you have y satisfying the equation, minus y will also satisfy, because you have a square of y here and there is no odd power of y. In fact, there is no other term involved in y. You have y square, so that tells you clearly that whenever x comma y, minus y is a point on the curve, you will also have that x comma, whenever you have x comma y, you have x comma minus y as well. So that is the very natural symmetry that we always have. So coming back to these non-examples, we have the curve y square equal to x cube, which looks like an arrow. The thing here near the origin looks like a tip of an arrow. And then these curves on, as you let x go to infinity, develop in this way. And here also we have this y square equal to x cube minus 3x plus 2. And again here we notice that there is a point of intersection where the curve intersects itself. Okay, and these are the points which are known as the singularities. So the singularities are the points where there is no unique tangent, and by unique tangent I mean there are more than one lines which can be drawn at that point, and their intersection with the curve is a single point. So for instance, here I may take the tangent of the curve in this way, as we are, we continue to go where where y is positive and x is going from 0 onwards to infinity, and then of course y becomes 0, and then y becomes negative and goes ahead. This will give you a tangent. Similarly, in the reflexive way, you will have x to be 0 again and y to be 0, and now x is going towards positive infinity, so y was negative, and then slowly y becomes 0 and y becomes positive. In this direction also we will get a tangent. So here we see that there are two tangents to the curve at the point, and therefore the point is a singular point. So this curve has a singularity at this point. Coming back to this point, here we of course have that the horizontal y-axis, x-axis cuts the curve on at origin. In fact, any line passing through origin will have only intersection with the curve given to be the origin. So here there are more than two. In fact, there are infinitely many tangents to this point. So in the algebraic geometric language, this point is called a cusp, whereas this point is called a node. So we should try to avoid these kind of singularities when we want to have elliptic curve. So we are slowly going towards the definition of elliptic curve. I have not yet defined elliptic curves for you. So what we have observed so far is that there is a y square coming, and on the other hand of the equation we have some equation in x, and that has been a cubic equation most often. And this is also not an elliptic curve. So here what I have done is that I have simply shifted this curve slightly to the left, so the intersection has become 0. The self intersection is 0. So this would, I guess, be given by y square equal to x cube minus 3x. We simply shift this to negative side, and so you get it to be 0, so that x equal to 0, y equal to 0 will satisfy the equation here. So these are the examples, and now we go and give the definition of the elliptic curve. So first of all, what we have learned is that an elliptic curve should have no singularities, and further it should be defined by an equation of the type y square equal to f of x. So that's a single variable on the right hand side, there is no y. On the right hand side it is a equation only in x, but moreover it is a cubic equation. So these are the examples that we have seen. If we go back, that you have y square equal to a cubic. This is how we demand that our curve should be defined, and moreover we have that there should be no singularities. So there has, of course, this is still not a definition, and we need to give the definition in the most precise way. So because we say that fx has to be cubic, I can write the polynomial f as ax square cube plus bx square plus cx plus d. This is the way we write it. And finally, there is this technical condition that the elliptic curve should have a point on it. So which means that there should be a solution to the equation that we have given above. So these technical conditions are very important conditions. To give you an example, when we talk about groups, we often, if you have to explain the notion of a group to a layman, what you would do is that you will tell that there should be a binary operation which should be defined on the set, and there should be identity element, there should be inverse element. These are the most important conditions, but there is a technical condition which is the associativity, and it is not very clear where we use associativity, but this is a very important condition. If you want to solve equations, say a plus x equal to b, that is where you are going to use associativity. And the purpose of having a group is to be able to solve equations. And here again, the purpose of elliptic curve is to do some nice things about it. So there is something called arithmetic of elliptic curve, and for that we should have that there should be a solution to the curve. This seems like a very technical condition, and it's not very clear where this condition is used, but we will see that this condition gets used. And if you don't have this, then you cannot do the nice things that we would like to do with the given elliptic curve. Okay, so these are the three things. First of all, it should be given by y square equal to cubic in x. There should be no singularity, and there should be a point. And having no singularity really means that this equation on the right hand side of the equality should have no repeated root. So when we consider this equation over complex numbers or over the field of the algebraic closure, then it should have no repeated root. Of course, you would perhaps know the way to check this, that the equation and its derivative should be coprime. That's one way to see that there is no repeated root. Now, this is the technical definition, that an elliptic curve is a projective non-singular curve of genus 1 with a rational point. So, meaning I understand that some of these terms may not be familiar with you, or even if they are heard of by you earlier, then it may have been a while since you dealt with them again. So let me just connect this definition with the previous definition that we have seen. No singularities means that we should have our curve to be non-singular. This is the way we connect uh, the no singularities with this definition. The equation should be here demanded that the equation should be given by y square equal to a cubic in x. And this really means that first of all, we are giving one equation. So there is a polynomial in x and y which is obtained by taking the difference of these two. Y square minus ax cube plus bx square plus cx plus d, whole thing put in the bracket. That is the polynomial in x and y that we are looking at, and we are looking at zeros of this single polynomial. So because you have one single polynomial and you are looking at zeros of it, we get a curve. Okay, if you had more variables and a single polynomial, then you would get what is called a hypersurface. So if you had three variables and one equation, then you would get a surface. If you had even further variables and one equation, then you would get a hypersurface. So the dimension of the structure that you obtained will be one less than the number of variables. Of course, meaning typically what we have is that whenever you are working over complex numbers, then you always have solutions, and by putting one value, so suppose I have a value for y, then I will get some solution for x, and therefore the independent value can be chosen to be the value of y, and so here the dimension is 1. If you had the equation to be an equation in 3 variables x, y, z, you will choose some values of x and y, and then you will get a polynomial in z which should have a solution, because over complex numbers we always have a solution to any polynomial equation. And then x and y being the independent variables, the dimension then would be 2. So you would get a surface. So here we are looking at 2 variables and one equation. That's why we get a curve. Now this genus 1 refers really to the conditions that we have on our equation. So going back with the definition, we have non-singular because there is no singularity. We have curve because there are 2 variables and a single equation. And now we are saying that it should be a curve of genus 1. So curve of genus 1 says that most generally this is how the equation should look like. So when you have a polynomial and it has some degree, so here the degree is 3, and if you get a curve, then the genus is obtained by taking the um, binomial symbol of degree minus 1, choose 2. So here, so typically for a polynomial of degree n, it will be n minus 1, choose 2, which will be n minus 1 into n minus 2 divided by 2. And so for 3, we get 2 choose 2, which is 1. So for a cubic curve, we get the genus to be 1. If you have a degree 4 curve and you are looking at the projective curve, then sometimes you again get a genus 1 curve. But we will not go into that right now. So that's what we have, that we should have a non-singular curve of genus 1. And there should be a rational point. This is the technical condition that we had here, that the elliptic curve should have a point on it. And now I should tell you why we are looking at projectivization. So whenever we have some equation over some affine plane. So for instance, here we have an equation having 2 variables x and y, and we have not told where we are looking for solutions, but understandingly we take the solutions over reals or over complex numbers. And so this is what is going to give us a figure, or the if you draw this figure, it will be drawn in R2 or in C2. So such things which are drawn in the vector space, n-dimensional vector space, either over Rn R or over C, so it will be Rn or Cn. These are called affine varieties because they are given by affine equations. And then we do something to get a projective version. So I think I have defined this somewhere later. So let me go ahead with the slides. So this is all in red because these are the things which were not defined, but we have now defined them. And so what we are doing is that we are looking at solutions of this equation where the coefficients, so the coefficient for y square is 1 and the coefficient in the polynomial for x are a, b, c, d. So they are coming from some field f. We are actually not going to restrict ourselves to the field of characteristic 0. So we will not look at only R and C. In fact, from your point of view, the most interesting fields are the fields of finite characteristic. You will be looking at FQ, the field with Q elements. Okay, so that is what we are going to look at. We are fixing ABCD from any field capital F, and we look at solutions to this equation with the property that the equation on the right hand side has no repeated root. This is because we need to take care of the condition that our curve has to be non-singular, and the genus 1 is taken care of because our polynomial is a polynomial in degree 3. And further, we also demand that there is a solution to the equation over f. This is because we want to have a rational point. Okay, so these are the basic things. We are looking at solutions to this equation where the right hand side has no repeated roots and the solution set over f is not empty. That means there is a point x and y again in the base field f itself, such that the x comma y satisfies the given equation. Okay, so this is what we are going to look at. Further, when we say that we are looking at the projective variety, so what we really mean by that is that we introduce one more variable, which we call z, and make this equation a homogeneous equation. Now the degree of this equation is 3 because the highest degree of a monomial appearing here is 3. So we should make the degree equal to 3 and we make it by multiplying by z to y square. So we have y square z. To the term ax cube we make no change because the degree is already 3. Then here we get bx square z cx z square plus dz cube. So this is now a homogeneous equation, although in 3 variables, but we have increased variables. So ideally what we should get here is a surface by the things that I have explained to you earlier, that we have 3 variables and single equation. And so if you choose any 2 points, then that will give you a third point. And so the choice of 2 points is up to your choice. So those are the independent variables, and so the dimension is 2. But we will not look at the solutions to this homogeneous equation in R3 or in C3. What we are going to do is the following, or here, more precisely, we are not going to look at the solutions only in F3, but on the solution set, we put some equivalence relation. So let me take 2 minutes and explain it to you, because this is important with respect to the point at infinity that will come later when we define the group addition, the group law, and so on. So let's look at the equation once again. It's an equation which is homogeneous. So suppose I have the point x naught, y naught, and z naught satisfies this equation. Then if I multiply x naught, y naught, z naught by a fixed constant, say lambda. All right, so we already know that x naught, y naught, z naught satisfy this equation. So if I put x naught and y naught and z naught in place of x, y, z, then we get equality. Now I multiply each of the x naught, y naught, z naught by a fixed constant lambda. So if I try to put the values lambda x naught, lambda y naught, and lambda z naught again in the equation, then the left hand side, which I have highlighted here, will give you y naught square z naught, and there is a lambda cube that will come out, because we actually are going to look at lambda y naught whole square into lambda z naught. So lambda will come out with a power 3. Similarly, here we will have a lambda cube x naught cube plus b lambda cube x naught square z naught plus c lambda cube x naught z naught square plus d lambda cube z naught cube. So actually in both the sides of the equation, we will have lambda cube as a common quantity. And if lambda is if lambda is 0, then of course you have equality, because you have both sides of the equation give you 0. And if lambda is non-zero, then you can cancel this lambda cube from both the sides, and the x naught, y naught, z naught anyway satisfied your equation. So you again get equality. Okay, so what we have done is that we observe that when you have a solution x naught, y naught, z naught to a homogeneous equation of this kind, the only thing we have used is that the degrees of all the monomials are now equal. That's the only thing we have used. You may look at any such general equation in any number of variables, in fact any equations, right? And if you have the equations to be homogeneous and you have a point satisfying the equation, then multiplying by any constant to all the coordinates of the solution will give you one more solution. of the equation. Okay, so what we then do is that this whole set of solutions which are obtained by multiplying by a single constant throughout to all the coordinates, and we put them in the equivalence relation. So we will say that x0, y0 and z0, the triple, is equivalent to x1, y1, z1 if you have a lambda such that x1 is lambda x0, y1 is lambda y0 and z1 is lambda z0. Okay, so this is the equivalence relation that we have put not just on the solutions of this equation but on the whole F3. Okay, and now the bad thing about this is that whenever you have any x naught, y naught, z naught, you multiply by 0 and you get 0, 0, 0. So anything is connected to 0, 0, 0 by this equivalence relation. And if you have equivalence relation, then if x0, y0, z0 is connected to 0, 0, 0, x1, y1, z1 is connected to 0, 0, 0, you would expect that x0, y0, z0 and x1, y1, z1 should be also related. But that need not happen, right? Because you can have x0, y1, x0, y0, z0 in some way such that x1, y1, z1 is not obtained by simply multiplying by lambda to all the coordinates x0, y0, z0. If you multiply by lambda to x0, y0, z0, all you get is a line passing through the point x0, y0, z0 and the point origin 0, 0, 0. And everything on the line is equivalent to x0, y0, z0. But you know, in the three-dimensional space, you have plenty of other points. So this problem says that we have not really obtained the equivalence relation, and the way out of this is to remove the problematic point. We remove the origin and we will look at x0, y0, z0, or we look at the set f3 minus origin. Okay, so we will look at x0, y0, z0 where at least one of the x0, y0, z0 should be non-zero. And then we put the equivalence relation. Then it works, because the problem was giving the problem came because we had the origin 0, 0, 0, which was, you know, making all points equivalent to each other. You know, this reminds me of the K3 lectures that Madhav Mukund just now talked about, and even there, if Mukund remembers it, we had to make some small adjustment to, you know, we had K groups, and the K groups to begin with, we have the group K0, and the K0 was defined by putting some such equivalence relation. And there also we had to make some adjustments. And if I remember, Krishnendu, one of our common friends, had asked me what would be the problem, and although I could not give him the answer at that time, I gave him the answer in the next lecture. So every time you define some equivalence relation, I think, you know, we have to be very careful, and we need to ensure that the relation we are defining is really an equivalence relation. Okay, so we have this three-dimensional space F3. We remove the origin and then we put the equivalence relation. The space that we get, that is called the projective plane. So that is denoted by P2 of F. And in that plane, we now consider the solutions to the equation that I have highlighted. So although in R3 or in F3, we are going to get something which is two-dimensional, but now we have put this equivalence relation where all lines are shrunk to a point. Therefore, this again gives us a curve. Okay, so this is the projective curve that we are talking about. I think let's understand this definition, because this is one of the very basic definitions. And you may wonder, what have we done to the original curve? Or when we were looking at the examples that I showed you in the pictures, those looked like normal curves. So what was the important thing there? Are they also projective curves? So this is what we are going to do. Yeah. So what we are going to do is, having defined the projective curve in this way, perhaps I should see if there are any questions at this point. Maybe I can go to chat and see if there are any questions. Okay, so after 143, I don't see any comment. So, all right. So, if you have any questions, you can continue to ask here, and I will come back to the chat from time to time and see the questions. Okay. So, coming back to our point, we are looking at this equation, and we looked at the solutions in the three-dimensional space. But on the solutions, we put the equivalence relation, and so we got a one-dimensional variety. So we got a curve. And now we want to understand, because projective spaces are very difficult to visualize. So we would like to understand these with the help of our usual pictures, planar pictures, or in some cases we understand varieties by having models in the three dimensions. So that's the affine. We would like to understand them by affine pictures. So we can actually recover our earlier equation, this one, simply by putting z equal to 1. But how are we allowed to do that? So let's recall that our equivalence relation will allow us to multiply to the x naught, y naught, z naught by any quantity. Correct? So as long as your z is non-zero, you can multiply that through play the point x naught, y naught, z naught by the constant 1 upon z naught. And you get a point where your last coordinate is equal to 1. Correct? As long as your z naught is non-zero, you are allowed to do this. We will see what happens when z naught is 0. But as long as z naught is non-zero, you can simply put z naught equal to 1, because you will still be in the same point as far as the projective space is concerned. You are multiplying the triple x naught, y naught, z naught by a fixed constant, non-zero constant. So you are looking at the same point. And so whenever z naught is non-zero, there are two types of points where z naught is 0 and when z naught is non-zero. So for z naught non-zero, you can simply multiply the triple x naught, y naught, z naught by 1 upon z naught. So the point x naught comma y naught comma z naught is equivalent to the point x naught upon z naught comma y naught upon z naught comma 1. So in the projective space, you have the same point, but in the affine space, you may understand it by having z equal to 1, and therefore you get your original equation back. You are simply putting z equal to 1 here. So you get y square equal to ax cube plus bx square, because z is 1, plus cx, z is 1, plus d. So we recover our earlier picture for the point z equal to 1, but then we have to worry about z equal to 0. What will happen when you have z equal to 0? So look at this homogeneous equation again, because that's where we are going to put z equal to 0. Any remark? Someone had switched the mic. Okay. I think I will have to start sharing again. So when we look at this homogeneous equation and you put z equal to 0, remember z as a variable occurs on both sides of the equation, on the left hand side as well as on the right hand side. And the only monomial, only term where z does not appear is this. But everywhere else you have z and you are putting z equal to 0. So you are going to get this highlighted term equal to 0. The equation now becomes ax cube equal to 0. But our a has to be non-zero. We have to take a cubic. If a is 0, we don't get a cubic equation. We will get a quadratic equation, and the genus will no longer be 1. The genus will be 0 for a quadratic equation. You know, the formula is n minus 1 into n minus 2 divided by 2. So if you put n equal to 2, you have 0 already in the numerator. And so the genus becomes 0. So that is not allowed. Therefore, a has to be non-zero. And now you have a into x cube is 0. A is non-zero. which should give you that x has to be 0. Okay, let me go through this again. When we had this equation in the homogeneous coordinates and we are looking at the projective space in 3 dimensions, then z is 0 and z is 1. These are the only two cases. When z is 1, we get our original equation in two variables back, and when z is 0, we are forced to have x to be 0. So the points will look like x comma 0 comma y comma 0, and because we should have non-zero points, y has to be non-zero. In fact, this equation is satisfied by any y where x and z are 0. Correct? So I can have any y and x and z equal to 0. We will have a solution. But remember that 0 comma y comma 0, because y is non-zero, this triple is equivalent to 0 comma 1 comma 0. Okay, so when z is non-zero, you can make z equal to 1 and you get your original picture back. When z is 0, you simply have a single point which is given by x equal to 0, y equal to 1 and z equal to 0. So this is what I have here. So we can recover our earlier pictures of elliptic curves simply by putting z equal to 1, and the extra point that we have is the point 0, 1, 0. This is a very important point on the curve, and we denote this point by this very strange looking symbol, which is a curly O, capital O, but it is curled somewhat, and this is the point which we are going to use to define our group law. Why is it called, this is called a point at infinity. So let's understand again why it is called the point at infinity. So remember our usual pictures which we have seen up to now, I think it is, yeah, so even here they are there. So but since I don't want to tell you already about the things which I'm going to tell, this is how the earlier pictures look like. And now we know that these are given by x and y on this curve, and z is equal to 1. Correct? So this plane is sitting in the projective space where your z is equal to 1. But this is a point 0, 1, 0 which cannot be seen on the plane because your z is not 1 here. But if you were to think about this, whenever you want to understand something, you are allowed to do things in a non-precise way. Just to make sure that we understand and we don't do any operation with that, we will just try to understand it. So to understand where this point sits on the plane, we need to make the z coordinate 1. And how do you get from 0 to 1? You divide by 0. It's not a very precise thing, but you are dividing by 0 to get the point at infinity, or let's not call it a point at infinity because we haven't really explained, we are in the process of this nomenclature. So let's call it O. We are trying to understand how this point O would look like if we were allowed to think in a non-precise way. So we should make z equal to 1, and by only by dividing by 0 we can make z equal to 1, right? And if you are dividing by 0, you should divide by 0 throughout. So this x coordinate will also become 1. But what happens to the y coordinate? Y coordinate becomes 1 upon 0. And that's the infinity that we are looking at. Okay, so this is called the point at infinity because it is really sitting at infinity. If you consider the stereographic projection of the sphere minus the north pole on R2, when you look at complex numbers, I think, my favorite book in complex analysis is the book by Conway. And I think in the very first chapter, it talks about stereographic projection. So the stereographic projection is obtained by removing the point at north pole, which is, I think, the point where your x is 0, y is 0, and z is 1, right? And then you draw lines from this top point with all the points on the sphere, and these lines will intersect the plane at the origin exactly in one point, and that's the image of that other another point from the sphere onto the plane. Okay, so that's the stereographic projection, but we have to be careful here a bit because x coordinate is not going to infinity. X coordinate becomes 1. Only the y coordinate goes to infinity. Okay, so when you consider the picture that we had seen earlier, if you draw a vertical line here, or you consider this y-axis for the sake of it, then this y-axis on both the sides, if you extend, it will go to infinity, and those are the points which are going to give our point at infinity. If you extend the x-axis in this stereographic projection, they also go to point infinity, but not in our projective space. In our projective space, only the vertical lines meet the point at infinity. Okay, so this is a somewhat non-precise way to understand how the point at infinity looks when you are looking at the projective spaces, but it's a very useful point of view. And the things that we do later on, we are going to use the pictures that we have in R2 or in the two-dimensional plane, but actually we are going to do things with the projective space. And there is consistency by understanding this, that only the vertical lines go to the point at infinity, not the horizontal lines. Okay, so once we have accepted that, now we go to the group structure on the set of its points. So these are the elliptic curves and the pain that we have taken in defining them in this very careful way, especially the genus being 1 allows us to have a very natural group structure on the set of its points. So let me tell you something more about these varieties. So, we have, what we have really is a variety. That means we have taken some variables, we have taken equations in those variables, and we are looking at their zeros. Those are the affine varieties. When we look at the homogeneous equations, or if you have an equation already, you make them homogeneous by introducing one more variable, and then consider the solution set, remove 0. 0 will be there because the polynomials are homogeneous. 0 will be there in all the solutions. So remove that and then put the equivalence relation. So what we get there, those are the projective varieties. So we have these varieties, and to any projective variety, there is something called as Picard group. So what you do is that you look at what are called divisors, and these divisors form a group in a very natural way. You can add them just like you would add two integers, and so you have the group called Picard group. But if you have a curve which is non-singular, and if the genus of the curve, by the way, genus is a term which is defined only for curves. It's not there for higher dimensional varieties. There are, of course, some things which people have tried to do to define the analogous notions of genus in higher dimensional varieties, but I think there are no interesting results there as far as I understand. So genus is something which is defined only for curves, and if you have a curve of genus 1, then there is a one-to-one correspondence of the elliptic curve and its Picard group. Okay, so this is the very nice coincidence. This is the very nice accident, you may say, happens when you have a non-singular curve of genus 1. And therefore, you can pull the structure of the Picard group as the group structure back to the elliptic curve, and use that to define the group structure on the elliptic curve itself. This is what we are actually doing. So you have elliptic curve. which is a projective variety. It's a non-singular variety. It's a non-singular curve, projective non-singular curve of genus 1. And therefore, there is a bijective map from the points on the elliptic curve to the Picard group on that elliptic curve. And using this bijection, we can pull the structure back. You see, whenever you have, suppose you have a countable set, yeah, and you define a bijection of this countable set with the set of integers. Then by identifying with the images, you can actually have the group structure on your set, because the point which is associated with 0 will work like identity. The point which is associated with 1 added to the point with which is associated with 2 will give you the point which is associated with 3. That's the way the group structure will act. But this depends on the bijection. If you change your bijection, then the group structure changes. And this is because you are only using a bijection. There is no very fixed identity. So what you have done by changing the bijections is that you have moved your identity around, right? So that is the thing which is true even for the elliptic curve. Here we can choose any point. You can fix the bijection once you have fixed the identity. Once you have fixed the identity, then there is the group structure which is fixed. So here you can choose any point on the elliptic curve to be its identity. And then with respect to that identity, we have a group structure. And this is why we demand that there should be a rational point on the curve. Because if the set of points defined over the base field is empty, then you can't have a group. This is something that this is hidden in the definition of a group. Sometimes people define group by saying that it should be a non-empty set and so on. But of course, in the actions of the group, there is the action for the identity element. So if you assume that group is a set satisfying those actions, identity, inverse, associativity, and closure of the birational map, then it follows that it should be non-empty, because you are demanding that the identity action should be satisfied. So there should be at least one point. This is the place where we use that technical condition that our group of rational points should be non-empty. Okay. So all right, we can fix a point, and once you have fixed a point, you have the group structure. And in fact, the thing that we are going to do now, there we are going to use this point at infinity as our identity. So our identity will be given by this point at infinity, and all the group structure and all the pictures that we will have will use the point at infinity as the identity. Okay. So this statement is a very important statement. In fact, this group structure is the thing we are after. That's the structure that we want to get out of the elliptic curve, and the way we have defined an elliptic curve makes it possible to have this group structure on it. Otherwise, you may ask, do we not have a nice group structure associated to other curves? Yes, we have a nice group structure associated to other curves, but for that you have to go to the Picard group, and then you don't have the group structure on the set of its points, but you have it somewhere else. It's like you have a set and you want to know whether there is a group structure on associated to the set, then you always have the group structure of permutations of that given set. But if you want to know more information, want to have more information about your set, then it would be nice to have a group structure on the set. And in fact, something like an elliptic curve, which is defined in a geometric way, if your group structure is also given in a geometric way, it will tell you more information about the curve itself. And this is why it is more interesting to study elliptic curves. Okay, so let's go and define this group structure. So for the definition, as I told you, we need to first define what our identity element is, and we define the identity element to be the point at infinity. This is our identity. Okay, now this group structure is defined in a somewhat funny way. it says that we want to actually, when we talk about group structure, we should be able to sum two elements. But here the description is given by saying that it will tell you when the sum of 3 points is 0. Okay, so now we can call this point as 0, although we have been calling it as O, but it's now our identity element, so we will continue to call it 0. So this is a very important statement again, that for any line intersecting the elliptic curve, the sum of the 3 points in the intersection is defined to be 0. Okay, so there are, what are the things which are going into making this statement? First of all, we are taking a line intersecting the elliptic curve, and then we say that there are 3 points in the intersection. So this is by a theorem of a mathematician by name Bezout, Bezout. So Bezout's theorem will tell you that when you have the elliptic curve and you take any line in the projective plane, there will be intersection of this line with the elliptic curve, and the intersection will have 3 points counted with multiplicity. So some points may come more than once. It's like when you have the circle and so let's imagine the usual unit circle which is there in R2, and I draw a line in the plane, and because we don't see things happening in the plane as they happen in the projective space, let us assume that our line intersects the curve. If you go to projective space, you will not have to assume this. This will follow by Bezout's theorem. But let's assume that for the moment, because we are working in R2. So you have a line cutting the circle, and we see that there are 2 points, where the first point where it enters the circle goes inside the disk, unit disk, and then as it intersects the circle again as it goes outside the unit disk. This is the general picture, but there could be some lines which are tangent to the circle, right? So there will be a line which will be tangent to the circle, and how do we obtain it? So for instance, you take the unit circle, which is the perimeter of the unit disk, and consider the y-axis. So y-axis is a vertical line which intersects the unit circle in 2 points, namely 1 comma 0, 0 comma 1 and 0 comma minus 1. And now we take lines which are parallel to y-axis, but where the x coordinate is positive. So if you shift your x coordinate from 0 towards 1, you will continue to get vertical lines parallel to y-axis, and they will intersect in some points. So let's call them, if they are given by the angle theta, you will have sine theta cos theta, comma sine theta minus cos theta. And you go on further, and ultimately you will reach the point x equal to 1. And now there are no 2 points, but there is only a single point, 1 comma 0. But that is where the line is tangent to the circle, and there we say that the multiplicity of the point is 2 because it is tangent. So whenever we have a tangent, we count the multiplicity to be 2, and for the point at infinity, sometimes we will also take the multiplicity to be 3. In fact, if you look at the whole thing in the projective space, so your line will be given by a homogeneous equation, and you actually write down the equations and solve for that, you will see that there are these roots x minus alpha, y minus beta, z minus gamma, dividing the intersection with the correct multiplicity. Okay, so that's why a tangent is said to have multiplicity 2 at the point when we are looking at it in R2. And in the projective space, sometimes you will have lines with multiplicity 3 at the point at infinity. Okay, so that says about the 3 points being in the intersection, and those 3 points can be the point at infinity. Those 3 points can be all the 3 points on your curve. It can be any such thing. These 3 points could be the point on the curve seen in the picture in the two-dimensional plane, or it can also be one of the point, could be the point at infinity. Okay, so we define it. by saying that the sum of 3 points on in that intersection is defined to be 0. So if you have 2 points P and Q, what we are going to do is that we will join these 2 points by a curve and take the third intersection point. So if your intersection looks like PQR, then we are going to define the sum of P and Q to be minus R. But how do you obtain minus R? For R, so for that we look at this. When you have a point P on the curve, then minus P is obtained by simply drawing a vertical line through P, because the vertical line will intersect perhaps in some another point on the curve, and because it is vertical, remember I told you that the point at infinity lies at infinity, but only when y is infinity. So if you take a vertical line that is parallel to y-axis, so two ends of those lines, one going up and the other going down, they meet at the point at infinity. So that point at infinity is the third point on the line. You started with point P on the curve. The third point is O or 0. And therefore, the second point has to be the negative of your point P, because P plus that second point plus 0 is 0. Therefore, the second point has to be minus P. So taking this as the definition, we can actually compute negative of a point by drawing a vertical line through the point and intersecting it with the curve in the picture in the R2. And then finally, if you have 2 points P and Q, the sum is obtained by continuing the line which joins those 2 points, intersecting it with the third point, and taking the point below that or above that in the vertical line. Okay, this is the definition of the group, and this is where we have the picture. So if you have the point P here and the Q where this blue line is vertical, then we have that P plus Q plus 0 is 0, because 0 is the third point on this vertical line, and the sum of 3 points in the intersection of a line with the curve is defined to be 0. And therefore, this will tell you that minus P is this point Q, or again minus Q will have to be P. Minus of minus P is naturally P. So if you consider this picture and you have a point anywhere and you want to compute its negative, you simply put a minus sign to its y coordinate. That's going to give you the negative point for that point P. Okay, so that is what has been said here in the bottom also. If P is a point on the curve, then minus P is obtained by simply drawing a vertical line through P and taking its intersection with the curve. This is how negative is obtained. Here we have that P plus 0 is 0, because at the tangent, the point comes with multiplicity 2. So the 3 points on this line intersecting our elliptic curve are P comma P comma 0. And therefore the equation reads P plus 0 equal to 0, and therefore the point P is of order 2. So the points of order 2 are precisely the points where the tangent to the curve is vertical. These are two statements which are converses of each other. I said that this P where the tangent is vertical is a point of order 2, but this statement also holds that the points of order 2 are the points where the tangent to the curve is vertical. If you wanted to have suppose you had a point here on the top, right? So I hope you can see my mouse. So this is where I am drawing, or let's say that I am taking the intersection of the curve with y-axis where y is positive. Okay, so that point is now well defined, and I want to obtain the sum of this point with itself. That is what I am trying to do. So let me call this point to be x, and I am trying to obtain what is x plus x. So the line which has x as multiplicity 2 is the line which is tangent to the curve, right? So I will draw a tangent to the curve, and if this picture is drawn carefully, then the tangent will perhaps cut this curve at a third point, which is here. So this point x with its added with itself plus this third point gives you 0. And this third point has its negative sitting here. So adding this point x to itself will give us this point. Okay, that is the way this addition is defined. And the whole nice thing about this addition is that this way, the addition being defined in this way, respects the bijection that you would get by the algebraic geometric results from the elliptic curve to its Picard group. Okay, and therefore we can define the group structure in this way. So the points of order 2 are precisely the points where the tangent is vertical, because we don't want the line to intersect on any other point in R2. It should go to infinity, and the points which the lines which go to infinity are the points which are vertical. So if the tangent is vertical and you have the points where the tangent is vertical, those are precisely the points of order 2. You will perhaps remember that we had obtained elliptic curve by pinching at these 2 points. And so we had obtained an elliptic curve where we had 2 distinct components. Let me go to that picture. So these were the 2 elliptic curves pictures that we had seen. Here, this is a point where the tangent is vertical. This is another point where y-axis is the tangent, and that is clearly vertical. And this is also another point where the tangent is vertical. So we have 1 point here, 1 point here, 1 point here. These are 3 points of order 2. And together with the identity element, these 3 will give you the subgroup z by 2z cross z by 2z. You get a group of order 4 of torsion 2. In fact, let's compute the sum. If I start with this point of order 2 and the origin, I want to sum these 2 points. So I will draw a line joining these 2 points, which gives you the x-axis. So the x-axis starting from this P and Q intersects your curve here, correct? So this point, if you call it R, negative of this point should be the sum of these 2 points. So if maybe I should have written here P and here Q and then R here, and then negative of this R is the sum of those 2 points. But this point is of order 2. So R plus R is 0, which means that R is equal to negative R. And therefore, this is precisely the sum of this point with this point. Similarly, if I want to take the point at here, I guess this is x equal to 1 and y equal to 0. So the equations are given by, so these 3 equations that we see here for y equal to 0 are given by the equation x cube minus x equal to 0. So they are at x equal to 1, x equal to 0 and x equal to minus 1. So if I add minus 1 and 0, I get 1. If I add 1 and 0, I will get minus 1 on the elliptic curve. And if I add 1 and minus 1, I will get 0, as one should get. 1 plus minus 1 is always 0. Right? So this is the Klein-4 group. So you have any 2 points which are non-trivial being added will give you the third non-trivial point, and each of the points is of order 2. And in fact, you cannot have more than this. In the real line, you cannot have more than 3 points which are tangent to each other, because the torsion 2 subgroup cannot be more than z2 cross z2. So maybe I'll tell about this a few minutes later. But what we have learned, first of all, is that negative of a point can be obtained by simply drawing a vertical line and obtaining its intersection in the plane with the curve. If your point is tangent to the vertical line, then it is its own negative, or it is of order 2. Here we have q plus p is 0. Therefore, if I wanted to add q to itself, I will have this p and then I will take its point below, which will be minus of p. That will be the, so sorry, I think this is, yeah, This is correct. P plus Q is minus of Q, or looking at it in the other way, if you wanted to add Q plus Q, it will give you minus of P. Okay. And finally, we have the general picture where P plus Q is negative of R, which is here below. So this is the way the group structure on the elliptic curve is defined. And since we have covered more than half of my allotted time, I would perhaps go and check if there are any questions. Mukund is pointing out that Krishnendu was the point of trouble in, yeah, maybe one could say Krishnendu was the singularity, but many times it is the singularities which make it very interesting. Mukund has also asked this question: does the idea of genus in terms of degree of elliptic algebraic curves coincides with the topological idea of genus? Yes, it does. But we have to consider them as the curves given in projective space. So looking at it, considering its topology is a bit difficult to understand. And we also have, does the name point at infinity in one point compactification come from this idea of dividing by zero in projective spaces? Yeah, more or less. In the one point compactification, it's the same as the stereographic projection. So if you take the plane and you want to obtain its one point compactification, it is by adding the point at infinity and then everything which is outside a compact set. So you may consider the disks around zero of large radii and you take their closures. So you have closed disks centered at zero of large radii. These are compact spaces, and everything outside that has to be something which is in a neighborhood of infinity, right? So the basic open sets containing infinity are the complements of compact sets in your space. That's how we obtain the one point compactification. So the points which are away from zero more and more, those are the points which are closer to the point at infinity, because they are in the smaller and smaller neighborhoods of the point at infinity, and that's how we get it. The notion point at infinity comes. And the question further, which came first, Picard group or the group structure on the elliptic curve? So this is also a very interesting question. We can go back and try to see, since I am continuing to share, maybe I could go back to slides. So if we look at the theory and or the history, I should say, and see where the elliptic curve and the group structure came about, it was Jacobi in 1835 who suggested this geometric way of defining the group structure. So my understanding is that it came before the Picard group was discovered. The more geometric way, our ancestors had a way to do with the geometry. And so Jacobi is the one who actually defined the group structure, who suggested that it can be done in this way. I don't know if he talked about the real lines, meaning the real picture, or the picture over finite fields. That I am not sure about. I will have to check the history carefully. But it was Jacobi who described this thing first. Then Picard group was associated to all projective non-singular varieties. And then it was observed that for the elliptic curve, this group structure happens to be the same as the group structure on its Picard group. So the chronology goes in that way. Okay, so once we have understood this general picture of the sum, I think it's now 2:30. I guess I have 15 more minutes, Mukund. Okay, great. So, when I made these slides, initially I was afraid whether I would be able to cover the time. My worry is always to be able to speak for the allotted time and not wind up my lecture in first half, 1 hour or so. But I think we are doing okay time wise. So, of course, we can't always draw lines and compute the intersections. In fact, if you are working over some very complicated fields can be really very complicated. It need not be the field of real numbers, complex numbers, rational numbers, number fields, local fields, or finite fields. You may have the fields of rational functions, for instance. You may take polynomials in n variables. over a field which gives you an integral domain, and then you take its field of fractions, that is a field. And now how do you do computations? You can't draw lines with that field, so there should be formulae. And because this is something which people can verify, I will not spend too much time about this. So if you have 2 points P and Q on your elliptic curve, so P is given by xp yp and Q is given by xq yq. These are the x and y coordinates. And we will also need the slope joining these 2 points. So suppose the slope is s. Then the third point can be obtained. Third point r with p plus q plus r equal to 0 is obtained by this simple formula, where the x coordinate is given by square of the slope minus the sum of the x coordinates of the points p and q, and the y coordinate of the r is given by y coordinate of the initial point plus s times the difference of the x coordinates of the initial point P with the x coordinate of the point R. Now, there is something which you may have observed already, and I have not written it here, which is that the group structure is abelian. Because it doesn't matter whether you are adding P and Q or you are adding Q and P. The order of the P and Q is not important, because the third point of the intersection is going to be the same point, whether you take the line as the line containing P and Q or you consider it as the line containing Q and P. The order of the points P and Q is not important. So it may seem that the y coordinate depends only on the initial point, but you can actually write down a similar formula which will give you the same coordinate, but instead of yp you will have yq, and here you will have xr and xq. I guess it will become xq minus xr. So you will just have to write it down carefully and see. So these are the coordinates of the point r, xr comma yr, and then the sum of the 2 points p and q is given by the x comma r and negative of y comma r. And when you have general case, this formula will work. In some special cases, what we need to do is that we need to be careful. If you are taking vertical lines, we don't know what is the slope of a vertical line. The slope of x-axis is 0. And what we know is that if you have two intersecting lines, the product of their slopes is -1. So is the y-axis slope negative infinity because it is -1 upon 0? What is the slope? Maybe it can be taken to be infinity, and then you have to be really careful. If you put infinity here in the equations of xr and yr, then you get weird things. So what we should then do is that do the computations carefully. So these formulae will work in the general case. Most of the times these formulae work, but in the special cases we have to be somewhat careful. Okay. Of course, when you compute the slope, sometime you may have to divide by 2. And therefore, whenever you take a field of characteristic not equal to 2, then the computations that we have done here, they remain valid. But if you are looking at a field of characteristic 2, then again you have to be somewhat more careful and obtain the points of intersection. We needed to compute slope because we want to have a formula for the point of intersection. If you are not able to divide by 2, that will tell you that you can't use the slope to compute the sum. You will have to do it in a different way. This is also done. The formula looks slightly messier, but it can be done. It is not impossible. And so over any field, this can be done. And if you now look at these things very carefully, if your xp, yp, xq, yq, these are in some field f, then s will be also in the same field, because how do you obtain s? You will take the difference of the y coordinates, divide it by the difference of the x coordinates. So you are in the same field, and therefore xr and yr are also in the same field. So what we have is that if your points P and Q are defined over any such field, and here by any such field I mean the field of characteristic not 2. Okay, so if you have P and Q to be defined over any such field, then so is their sum. So of course, when you take the F bar points, the points over algebraic closure, and you have this group structure, then the formula will tell you that the sum of any 2 points defined over F will also have coordinates which is in the field F, which means that if you are taking the F rational points, so F rational points are precisely the points where both the coordinates are in the base field F. Okay, so you take the set of all these points together with your point at infinity, don't forget that point, then what you get is a subgroup of the whole group. And these subgroups are interesting when we consider some very special fields like the complex numbers, real numbers, rational numbers, and of course, from your point of view, the finite fields. So what we are going to now consider is to, I will very briefly give you some information about the rational points subgroups over for elliptic curves over these fields. Of course, for complex numbers, we don't have to take subgroup. It is the whole set of rational points, the complex points on the elliptic curve. Topologically, it looks like a torus. And this is where the genus comes. So elliptic curve over any algebraically closed field looks like a torus over that field. So it has, topologically, it has the structure of S1 cross S1. And we all understand that that torus has genus 1. This is the topological torus. This is not the algebraic torus that Mukund was referring to earlier. But this is the torus. And this torus will also tell you that, points of order 2 cannot be more than 3. Because it is S1 cross S1, and the finite groups, the finite subgroups of S1 are the cyclic subgroups, and therefore the finite subgroups of S1 cross S1 are given by finite in one copy cross the finite in the other copy, and there we see easily that the points of order n give you a subgroup which is isomorphic to Z by Nz cross Z by Nz, and therefore the points of torsion 2, I should say torsion, not the order. The n torsion subgroup is Z by Nz cross Z by Nz, and 2 torsion in this very special case is Z by 2Z cross Z by 2Z. And taking out the identity element, there are only 3 points which are of order 2. So over complex numbers, you have exactly 3 points of order 2. Sometimes these may even be defined over real numbers, but they may not always be defined over real numbers. So in the curve given by y square equal to x cube minus x plus 1, only one point is defined over real numbers of order 2. The other points will have complex coordinates. Whereas for the other curve here, which has 2 connected components, all the 2 torsion points are defined over real numbers. So this is the reason that we cannot have more than 3 points of order 2 over algebraic closure, and therefore over any base field. And the bijection, the homeomorphism of the points of elliptic curves with the torus is related to this very fantastic theory of Weierstrass on elliptic functions. And there is also the Ramanujan delta function, which plays a very important role in this. And over the field of real numbers, the curve looks very much like the curves that we have drawn earlier. If you take the general definition that it should be a projective non-singular curve of genus 1 with a rational point, any such curve can look in a very weird way. But you can choose your coordinates in such a way that the curve looks like the curves that we have drawn earlier. Okay, so your choice of coordinates will make the curve look like the curves that we had drawn earlier. So this is essentially what we have over complex numbers and real numbers. interesting things start when we consider rational numbers, so Q, and over other number fields also. So, often you may wonder that you have equations given over the field F, then why is it necessary that you don't have a solution to that? Especially, when we consider that any cubic over R has to have a real root and so on. So such a thing certainly is not true over rational numbers, and here is a very nice example of a genus 1 curve which is given by Selmer, and now it is called Selmer curve. In fact, there are a whole set of such curves which are all called Selmer curves. So Selmer gave this example of a homogeneous equation in three variables: 3x cube plus 4y cube plus 5z cube equal to 0. These numbers 3, 4 and 5 are very important, and one can show that this has no rational point. And the proof, there are some, you may just search on Google for Selmer curve, and you will see many interesting small articles given by people. Some use quadratic reciprocity law, as I think Mukund was referring to earlier, some of the very delightful things in number theory. You can use them to show that this equation has no rational point. So we have to be really very careful when we work over fields like rational numbers or other number fields, not like R and C. Over C, of course, every equation will have a solution, and over real numbers, once you take a y, then you have a cubic, and a cubic will always have a real root. So those are the fields where we don't have to worry. But over rational numbers, we have to worry. But when we have an elliptic curve, that means when you have a rational points on the set of elliptic curve over Q, then this subgroup, the Q rational points, that is a very interesting group. It is actually definitely an abelian group, but it is a finitely generated abelian group. The curves over complex numbers, as we have seen them, that is a torus, which is not a finitely generated abelian group. Okay, that you may perhaps have to convince yourself with that. You may think about it saying that R is not a finitely generated Z module. That is something which goes into proving that S1 is not a finitely generated abelian group, and so S1 cross S1 cannot be a finitely generated abelian group. But over number fields, because things are bounded in a very nice way, we have this thing which is called the Mordell-Well theorem, which tells us that the group of Q rational points is a finitely generated abelian group. So in fact, it will, by the fundamental theorem, the structure theorem of finitely generated abelian groups, it is going to be isomorphic to a few copies of integers, direct product with a finite abelian group. And so once we have an elliptic curve over rational numbers, you would want to know what is the corresponding R, what is the corresponding capital G, and there are many interesting results and very interesting conjectures related to this, which drive a lot of research in number theory. So there is this Birch and Swinnerton-Dyer conjecture, which talks about the rank R. So this number R is related to the elliptic curve also in a different way. So there is a way you can define a function, a complex valued function, which is called the L function of the elliptic curve. And this L function, this is not an analytic function. It will have a singularity at the point z equal to 1, if my memory serves me correct. And it's a removable singularity. So it's a pole of certain order, and the order of the point z equal to 1 as a pole for the L function is equal to this R. So it's a very far-reaching conjecture, and we don't know how Birch and Swinnerton-Dyer, these two mathematicians, came to making this conjecture. There is the algebraic rank, which is the number R, which we have in the previous slide. And there is the analytic rank, which is the order of the point z equal to 1 as a pole for the corresponding L function. and then we want to say that these two numbers are the same. And in fact, interestingly, this conjecture has been proved in many cases. I think when the order is zero, that means it's not, sorry, so I should not have said removable singularity, it's a pole. When it is a removable singularity, then the group should have rank to be zero, and so it should be simply a finite abelian group. That has been proved. So when the analytic rank is zero, it is proved that the algebraic rank is zero. I think it's also proved that when the algebraic rank is zero, the analytic rank is zero. And for one of the two to be equal to one, the other implies one. That is also proved. So I don't have the exact knowledge of the current status of this conjecture, but more interestingly, perhaps you would be interested in knowing that Manjul Bhargava has proved this conjecture in probability. So what Manjul actually proved is that probabilistically this conjecture holds true. And in fact, he went ahead by saying that probabilistically the rank of the Mordell-Well group, this is called the Mordell-Well group, is 1.5. So that is a very interesting observation that Manjul has made. His Fields Medal citation included this work. This is the work with my grandfather academically, Deependra Prasad's advisor, Benedict Gross. So they together have made this very nice work on the BSD conjecture. And the next things that we have are the theorems of Mazur and Merrill. Mazur is the mathematician Barry Mazur from Harvard University. I think he was also a topologist earlier, but thankfully he got interested in number theory and he did a lot of interesting works in number theory. So what Mazur did was to compute all possible finite groups that you can have in the Mordell-Well group. So what are all possible Mordell-Well groups that can occur? That has been computed by Mazur. It's a cyclic group that can occur there, and I think the maximum order of that cyclic group is 15. But you of course don't have everything from 1 to 15. You have some of them, maybe 12 or 13 are missing. So that is the interesting result of Mazur. And then Loic Merel, a French mathematician, went ahead. Loic Merel is a student of Joseph Oesterle, and he went ahead and done Mazur, and he proved that for a number field also the cardinality of the Mordell-Well group, if it is finite, is bounded, and so those are precisely the uh, finite abelian groups that can occur as Mordell-Well groups of elliptic curves over number field. That is Merrill's work. Taniyama-Shimura Weyl conjecture, or what is also now known as the modularity theorem. This is a very interesting thing. This is proved by Wiles, Taylor, and now a bunch of mathematicians, including Taylor, of course. Taylor has been the principal investigator of this conjecture. And this conjecture says something about the elliptic curves and modular forms with the Galois representations and L functions thrown in. So these are some of the very interesting concepts in number theory, and they relate all the way to Fermat's last theorem. So I will perhaps not be able to tell about this, but many Indian mathematicians have written nice articles on this. I think Parvati Shastri, a mathematician from Mumbai University, she has written something about this. Deependra Prasad is an expert on algebraic number theory among many other branches of mathematics, and he has some articles. And there are now many nice books which are available on Fermat's last theorem, and you can read a lot about these. Not to talk about the various online fora like Stack Exchange, Math Overflow, Quora, and perhaps also Wikipedia. But you have to be careful because Wikipedia, anybody can go and make any changes, and those have to be noticed by experts to make them correct. But certainly Stack Exchange and Math Overflow, these are the two fora which I use quite a lot, and I would recommend them to you also. If you work over finite fields, there is a theorem by Hasse which says that I told you that the number of torsion points is bounded because the group over algebraic closure looks like S1 cross S1. So the R torsion points cannot be of order more than R square, but it is of course not clear how many of these are achieved below. And what we have moreover over finite fields is that the whole set is finite, meaning your field is finite. The three-dimensional space over the field FQ will have Q cube points, so that is finite. And then the projective space is obtained by putting some equivalence relation, that is a finite set. So ultimately the group of FQ rational points is going to be a finite set. And what better invariant of a finite set we can have than its cardinality? So we would like to have how many points can there be over FQ, and that hash EQ. So E is the notation for the elliptic curve. It is defined over FQ. So EQ denotes the set of FQ rational points, and hash denotes the cardinality. So this cardinality is very close to Q plus 1, and the error term is in terms of 2 root Q. So it is of slightly lower order. The cardinality is roughly of order 1 if you look at it as a polynomial in Q, and the error is given by of order 1 by 2. And there is this very interesting conjecture by Sato and Tate. It tells how this error term varies in comparison with Q. So how this difference varies with 2 root Q. What is the error here, and how does that vary in comparison with Q? There are some very nice conjectures made by Sato and Tate, and some of these are proved, but to the best of my knowledge, the whole thing is not yet settled. And of course, you will have the RSA crypto system, which uses the group of FQ rational points on the elliptic curves. And with that, I come to the end of this lecture. So thank you very much for your time and attention. And thanks again to Mukund for inviting me to give this talk. So I could perhaps stop the.
Thank you so much, sir. So there are two questions from Mukund sir. First question is, in case of elliptic curves over finite field, the operation becomes just an algebraic expression in the coordinates involved. Can one think of defining more operations offering similar level of computational complexity, but not necessarily resembling elliptic curve formula?
That's a very interesting thought. I have not thought about this. So what you would want to do is to have operations on elliptic curves. So you would like to have something like a birational map, which takes the elliptic curve, cross elliptic curve to itself, and you would like to. So meaning if you wanted to do it geometrically, you would want to. You can. Here we used straight lines. Instead of using straight lines, you may want to take another. Yeah, it is very difficult to think of it. I actually don't know. The most honest answer would be that I don't know.
Okay, sir. So
And
there's
this,
one more question from Mukund sir. That do the coefficients of the Selmer curve relate to Pythagorean triplets?
no. That doesn't actually. In my belief, the very thing about 3, 4, 5 is that they are algebraically independent. If you are looking at them, in the sense of prime numbers, meaning you look at their primes. If you have three numbers which have all three are co-prime to each other, then I believe that you will still have the Selmer curve. But I will have to go back and check. To the best of my understanding, the Pythagorean triple property of 3, 4, 5 is not related here.
Yes, sir. So there are no more questions. Thank you, sir, for giving us this opportunity to hear your excellent session. It is a matter of honor for all of us. And the way you delivered your session, it was so engageful that personally I lost all track of time. So thank you. This FDP would not have been possible without you.
You are welcome.
So
You are all welcome. Thanks a lot to Mukund again, and thank you very much to you for coordinating this session.
thank you.
Program and keep
We will be in touch, of course. Yes.